How's it going? I was thinking about this the other day, and it made me wonder, how did we discover the core of the Earth? The core of the Earth is inaccessible. Realistically, we will probably never be capable of going to it. So, how can we determine so much detail about a location we cannot reach? The answer to this lies in seismic waves. To start off, let's imagine a sound wave. Sound waves propagate through compressible media, such as air or water. When an earthquake occurs, some of its seismic waves propagate through the earth in a similar fashion. These are known as P waves. They vibrate in the direction they are moving, squishing and expanding the earth as they go along. They do this while also moving rapidly at around 5 kilometers per second in a rock like granite and up to 14 kilometers per second in the densest parts of the mantle. There is a second type of wave emitted through the earth as well. This is called an S wave. These are slower transverse waves, meaning they move from side to side, like a rope moving one end up and the other end down. Unlike the P waves I mentioned earlier, they cannot travel through a liquid. This distinction proved essential in helping us to better understand the Earth's core and its composition. Let's imagine for a second a large earthquake is occurring. The P waves will lead the pack, shooting on ahead, with the S waves following behind at roughly half the speed. Now let's say we are observing data on these waves from seismometers in various locations. Both types of waves will be detected by our seismometers, but in the space where the waves travel to reach our distant measuring stations, a so-called shadow zone seems to manifest itself. Now, if you were starting from the quake's epicenter, and you were to travel about 104 degrees around the Earth's perimeter, all signs of the waves would disappear. But if you were to progress a little bit further, to about 140 degrees past the quake's epicenter, the P waves will begin to reappear, but with no accompanying S waves. In the early 1900s, geologist Richard Oldham realized the implications of this odd shadow. Using data that had been accumulated over the previous few years to probe the interior of the Earth, Richard surmised that the observed P and S wave behavior could be explained if the center of the Earth had liquid. His breakthrough led to the image of a molten core. This would become widely accepted until 30 years later, when seismologist and geophysicist Inge Lehmann came along and realized that his idea was perhaps a bit too simple. Inge surmised that had Oldham been accurate, then the refraction of the P waves by the dense liquid in the center of the Earth should have produced a total shadow. But measurements made with more sensitive seismometers of her day showed otherwise, with faint P waves still arriving within the shadow zone. Inge proposed that these waves were being reflected off of a boundary between an inner solid core and an outer liquid core. She published this in 1936, and it was confirmed 2 years later by Benno Gutenberg and Charles Richter. These two were able to accurately model the effects of a solid core. However, direct measurements of her findings would not come until 1970, when even further sensitive seismographs detected waves deflecting off of the solid core. Additional studies have been conducted beyond this point, which have furthered the proof of a solid core. Even so, we cannot truly be certain of the exact nature of the Earth's core, but I still find it fascinating how we can learn so much about places we are unable to visit. If you enjoyed this, please like and subscribe, and I implore you to step outside tonight and look towards the stars.